So again, we'll continue with the fundamentals. So we'll continue with the. So now onwards, whenever you have been given a number like 0000h, this doesn't mean these are 4 bits, but rather it's in hexadecimal number system, and this corresponds to 0000000000000000. Each nibble corresponds to one of the digits. So this corresponds to the equivalent of this 0000. This corresponds to this one, and so on. So you will be telling like the program counter points to the value, the program counter register points to the value 1234h. That means it actually points to the location 1234, but the equivalent value is 0001, 0010, 0011, 0100. So this is the equivalent value. You have to understand that. So in hexadecimal format. So whenever some number is given to you with telling like h is there, or it may be also told like 0x1234. This means that number is being represented in hexadecimal format. That is what you have to understand. And the equivalent binary also you have to see. So hex to binary and binary to hex. Always remember, this is what we are going to work with. Now, if you want to convert a number, a hexadecimal number to its decimal form, because we always do the works in decimal. Okay. So what we will do is, what you have to do is, if suppose you have been given a number like 23h, and you have been asked to find the, you want to work with some kind of operations. So first convert it to decimal. So what is the decimal? 2 into 16 plus 3 into 16 raised 0. 2 into 16 plus 3. So that will be equal to 35. Then operate whatever operation you want to do in decimal and then convert it back to hexadecimal. Why I am telling this is, suppose there is an example. If you want to add between two numbers, 45 in hexadecimal plus 67 in hexadecimal, and you want to find the equivalent equivalent hexadecimal value. So this one, the answer is actually AC in hexadecimal. How I got that AC? 7 plus 5 is 12. 12 in, if we are doing in decimal, if we are doing 45 plus 67 in decimal, how we will do? 7 plus 5 is 12. That 12 symbol is not there in decimal number system. So we will write 2 with a carry 1. So 4 plus 1 5, 5 plus 6 is 11. So we will write the lowermost position 1 with a carry 1. That is how we will get 1 1 2. But in the case of hexadecimal number system, 7 plus 5, 12. That corresponds to a symbol in hexadecimal number system. What is that symbol corresponding to? It is C. And 6 plus 4 is 10, which corresponds to a symbol AC. Now, if you are not very comfortable doing this operation in hexadecimal, you can either convert this to binary and then do the addition, which will be again tedious, because 8 bits plus 8 bits you have to do the addition in binary and then convert. Rather, you can do the same in decimal also and convert back. So what is the decimal of this one? 69 plus 103. You see what exact, whether it is correct. So the equivalent value is 172 in decimal. Now you convert this to hexadecimal. So 172 by 16 is 16 into 10 is 170, and the remainder is 12. So this corresponds to A and this corresponds to C. So any way you can do. So this will be equal to ACH. So convert from hex to decimal, then convert from hex to decimal, then do the operation, then you convert it back to hexadecimal. So that is how that is also one way you could do. So this is the thing which I wanted to tell you with regard to the hexadecimal format. Now let us see a simple program in 8051 assembly language. So this is a simple program for adding two numbers. The two numbers are, we are going to fetch it from the external memory location 4500 and 4501. So in the external locations 4500, we'll have a number 01. In 4501 we'll have the second number 02. We want to add these two numbers. We have to write the program in such a way that these two inputs are read from these two memory locations, and then the program will sum the two numbers and the result will be returned to location 4502. After executing the program you should get 3. So this is what the program is supposed to do. So I'm not. We'll see about the details about the program later. My aim here in this program is to make you understand about the 16-bit values and what are the registers that are going to be associated. So that is the primary intention. Programming part we'll see later. So what I'll just briefly explain about the program. The instruction set I will be sharing with you. So since this is external memory, the inputs are going to be saved in external memory and the output is going to be saved in external memory. You have to use a register DPTR. So that is the first thing. So like we studied how many bits this correspond to. So hash means it's an immediate value, constant value. In 4500 location, DPTR will be loaded with the value 4500. So 4500 corresponds to how many bits? 16 bits. Why? Because each of those digits 4500 corresponds to a nibble or 4 bits. So DPTR whole together will contain 16 bits. Then we are loading that value, moving that value to A pointed by DPTR. So that means address. From the address pointed by DPTR, load the value to A. So this is the destination register or variable. So just understand, you are going to get the first number in A, then that number is going to be moved in another register which is called R0. So R0 will be having the first number which will be equal to 01. Then increment. So DPTR will be incremented. It will be 4501. Then you will be taking the second number in A. So A will be having the second number, that is 02. So this means pointed by DPTR, from that address take the value and put it in A. Now add the two numbers A and R0. So you will get 3 and that will be saved in this A itself. This is the destination register. So A will be equal to 03. Then you are incrementing the DPTR. DPTR will point to the next location which is 4502. Save that value. What is the value of A? Put it in at DPTR. So at DPTR means in that address given by DPTR. So you will get in 4502 you will get the value of 03. So this is the program. So here if you see, you have used DPTR register whose value is initially, this is called data pointer, whose value is initially 4500. This corresponds to 16 bits. Then each of those numbers, that is from 4500 you got 01. This corresponds to how many bits? 8 bits or 2 nibble. Then you have 02, which again corresponds to another 8 bits or 2 nibble. Then you had put that in registers A and R0. What is the size of each of this register? Each of this register had a size of 8 bits. Then you calculated the sum and you put it back to 4502. So what is the size of the location 45002 4502? Each location can save 8 bits. So that is the size of the memory location. So this is what the program mean, the concept of the a simple program where we saw how to add between two numbers. Okay, we'll see about the instructions and everything later. Why I have taught this now is to just make you understand about the hexadecimal values and how each register will be saving how many bits and so on. So I will be showing this in a simple emulator for microcontroller programming, where I will show you okay how exactly these values are being saved, what is the size of those values, and what exactly how exactly it gets loaded to the registers and so on. So this is called RIDE. This software, whatever I am running, it is called RIDE. So this is a simple emulator for doing the microcontroller programming. So it's a simple emulator. So the same program whatever I explained, I have shown it here. So now let us run it and see the registers and the values. So these are some of the windows. When I ran, this highlighted line means the program execution is getting stopped here. Okay, so in the first line the program execution is waiting. So let us see how exactly it works. So where our data is supposed to come? Our data is supposed to come in the external memory locations 4500 and 4501, which I have mentioned. So this window corresponds to that external data memory. Okay, external data memory, and this corresponds to our code memory. Okay, so we discussed in Harvard architecture we have a separate data memory and code memory. So this corresponds to the Harvard architecture where we are having a code memory separate and data memory separate. So the code will be written in inside the code memory of the microcontroller, and this data I am fetching from an external world, okay, or external memory. So our data is supposed to be in 4500. So I am typing 4500 in the search button and clicking. So you will go to that memory address. The value there is FF. So double click it. I should get put the value 02 there. Then the next location corresponds to 4501. So 02 enter. Then only it will get loaded. Then the next location will be 03. Enter or plus tab. So you will get, we have inserted for 4500 location 02 and 4501 location 03. So what is the size? Each of this memory location is having 8 bits. Okay, so we have saved that. Now this is the program. We have typed that here. We have builded it or compiled. Now if you see the code memory, so this is the code memory. So in code memory, if you see the first line is move dptr comma hash 4500. The corresponding machine language for that is 904500. So I had told previously itself, the computer or the microcontroller or the processor understands only the language of numbers. The assembly language or the high level language we are using for our understanding, for the understanding of humans, okay, for our ease of use. So that is what we are using. So when we are writing move dptr comma hash 4500, there is an assembler sitting there which converts this into the language of numbers. Okay, so it is like you want to communicate between two people, but one understands only English, the other understands only Hindi. So what you will do? You will have an interpreter in between who will take the language of language whatever the first person is telling, which is English. Then he will translate that to Hindi and give it to the other person so that the other person understands. Similarly, the assembler will take this assembly language, convert to the language of numbers and give it to the microcontroller. So the equivalent assembly language for this move dptr comma hash 4500 is 904500. So this is the equivalent machine language. So how many bytes is this one? Like in the number system when we studied. So this corresponds to 00 corresponds to a byte, 45 corresponds to another byte, 90 corresponds to another byte. So we have 3 bytes for this single instruction. That is the machine language. So in machine language we have 3 bytes. So where those 3 bytes will be saved? I had told each memory location will save 1 byte. So 0000, one byte will be saved. 0001, the next byte will be saved. 0002, the last byte will be saved. It can be in the reverse order also. So let's not make it complicated. So there are 3 bytes. It will be saved in 3 locations. That is why the starting address is 0000, but the next address, this one, it is 0003. Why it is 0003? Because 0000, 1 byte for the first instruction. There are 3 bytes which will be saved in 0, 1 and 2. Now it goes to the next instruction will be saved in the location 3. So MOVX A comma at DPTR. What is the equivalent machine language? The equivalent machine language is E0, which is 1 byte. So it will be saved in 3. What is the next location the machine language will be saved? It will be in 4, because in 3 1 byte will be saved, next is 4. In 4 again, what is the equivalent machine language? F8. So F8 will be saved in 4. So the next will be in 5. Increment DPTR, the equivalent machine language is A3, that will be saved in 5 and so on. So like this it goes. So this is how the instructions are going to be saved in the code memory. Now let's run line by line. So these are the main registers. Like we had already discussed, the program counter is a 16-bit register. There are two registers which are 16 bits mainly. So one is the program counter, the other one is a data pointer. So data pointer 4 zeros means it's not 4 bits. Rather, each 0 corresponds to a nibble. So 4 into 4, 16 bits. Here also 4 into 4, 16 bits. So that is how the two 16-bit registers are. Now let's do line by line. I am going to execute line by line. So executing line by line is F7. So I am pressing F7. The blue line denotes the next instruction that is going to be executed. So here after I press F7, this will be executed. So F7, I pressed F7. So now if you see DPTR value is 4500. That is what the first previous instruction did. Now here also it goes to the next instruction to execute, which is E0, loading the value from 4500 to A. So what is the value in 4500? 2. What is the value in current? Now in accumulate it is 0. After executing this instruction, accumulator should be loaded with 2. I pressed F7. So if you see accumulator is 2. DPTR again we haven't incremented, so it is 4500. It goes to the next instruction R0. So it is going to execute that. What is the value of R0 now? So if you see R0 is 00. After executing this instruction, R0 became 2. Now the next instruction is increment DPTR. So DPTR incremented to 4501, 16 bits. Then we are loading that value to A. So A becomes, accumulator becomes 03. This value from 4501 is loaded to accumulator. Then we are going to add A and R0. Now the value of A is the second number, which is 03. R0 is 02. After adding F7, it becomes 05. Now we are going to increment the DPTR. I am going to press F7. So DPTR is 4502. Now we are going to load the value from A to DPTR. So here in 4502, the value has to be loaded. F705. So 05 came to that location. So this is a basic example of how exactly our microcontroller works, where we have the program, then we have the data memory, we have the code memory. So code memory, you will be see the microcontroller, the assembler will convert it to the machine language, and it will save in the respective locations. We have written 00H, that is why the program memory started saving in 0000 location onwards. This is 16 bits. Each of this address, the address of the next instruction to be executed will be coming in the program counter. So if you see, the program counter has incremented up to the next value of program counter is 0008. So that is what the next value of the program counter. It takes the address of each of the instructions. I'll show that once again. So let me restart it. So initially program counter is 0000. Then I'm not changing any value. Actually, we should give here 02, 03. So let us run line by line F7. So now if you see, program counter is 0003 to the next instruction, pointing to the next instruction. Then 0004 next instruction, 0005 next instruction, 6, 7, 8, 9, and finally the last instruction is in the location of 000A. So the program counter, after executing the instruction, it remains, it comes to 000A. So that is the significance of program counter. We have other registers also, which we will be seeing subsequently when we are doing the programming. Thank you.